Okay, welcome to the webinar. Thanks everybody for logging into this. The first slide here is just showing you a few hints and tips. Hopefully everybody can hear us properly. Microphone's usually muted as a matter of default, which helps with everything. There is a reconnect button that you can use, and the presentation slides. Underneath the slides, there is a place where you can post questions. If you wish to post the questions, we'll take those at the end, or if there's something that we really should cover during the presentation, then we'll take them there. There's also a chat function that you can use for any other communication you think is needed on that one. Okay, so without further ado, I think we'll just crack on into the presentation now. Okay, so this morning we're going to talk to you about the partial discharge monitoring and avoiding failures using permanent PD monitoring. So myself, Neil Davis, and my colleague Brad Monaghan are going to talk about that. We'll share the presentation duties over the course of this next 30-40 minutes. Okay. So the contents, we'll briefly talk about the condition monitoring and partial discharge, why we use those, the reasons for it, and some of the theory behind the different types of PD that we can come across. We'll talk about the handheld PD detection. So first, protocol normally for carrying out partial discharge and using PD for managing of assets is using handheld equipment, which is very, very valuable, and we'll show you how that works. And then we'll start looking at the testing intervals and some case studies through that. So the testing intervals are why you may win, how often, how frequent you may need to do handheld, and where the case is for pulling in permanent monitoring, showing you the benefits of permanent monitoring. All the way through that, we'll give you different case studies, show you examples of what we've been finding over the years. We'll have a formal section at the end where people can post questions. So like I say, if you use the question section at the bottom of the webinar, we'll take those and we'll be able to go into a bit more detail if you require it on that.
Maybe just check about the polls.
The polls, yeah. There are 2 polls underneath here as well. So if you go underneath, and you'll see 2 polls. One's we recommend if you could look at that at the beginning, which is just asking you how much experience you've got on there, so we can gauge what sort of level we're looking at, and how experienced you are in terms of partial discharge. And there's another one, if you can do that at the end, which is looking at what further topics you may want from us to do in future webinar. Okay, just a very brief one about EA technology in case you're unfamiliar. EA technology started off as the Electricity Council Research Centre of the UK electricity industry back in 1966. And through that time, we actually started working on non-intrusive and partial discharge detection in the 1970s and 1980s. By 1990, the privatization of the UK electricity industry started occurring, and EA technology, a couple of name changes, emerged eventually by 1994 as EA technology. And then 10 years later, there's a staff buyout. So we're now an independent employee-owned company. 2009, we opened the office here in Brisbane. So we've been going now for 11 years here. And the focus is no longer just on the UK. Obviously, we're 5 offices around the world, and working very much with electricity companies and owners, operators of high voltage networks, process industries, and everybody completely globally now. Looking generally at asset management, management of assets, and also the future networks and the transformation of the grid. So that's EA technology in a nutshell now. So an employee-owned independent company. So let's start with condition monitoring and partial discharge. So the reasons for, so we're coming at it really from two different aspects. So people who are going into the substations, obviously one of the big things that we want to know is to have confidence in the safety and the continuing safety, reliability of the assets that we're working on and around. At the same time, we have over the years in the electricity industry, and you see it in process industry, where often there has been a case of time-based maintenance where it's been maybe going into the assets a little bit too frequently. So if you're going to start moving towards extending those maintenance intervals, you really need to be in a defendable position. So using condition monitoring can be a way where you can start pushing out maintenance intervals and targeting maintenance where it's needed rather than just on a pure time basis. The whole point is really to prevent these unexpected failures and outages to the network. From an asset management point of view, we're looking at management of risk. So we want to de-risk, we want to prevent failures, reduce the probability of failure, and keep the network working in the most efficient and optimum way that we can. Sometimes we want to extend the life of assets, reduce capital expenditure, and we can do that, de-risking it by reducing, again, the probability of failure using condition monitoring. And of course, as soon as you put assets onto the network, sometime in the future, they will become to a stage where they're no longer fit for purpose. We need to take them off the network. So using condition monitoring can be a way of prioritizing that and determining which is the optimum replacement time for switchgear, for cables, transformers, etc. So that's really why condition monitoring is used. If we look at the objectives of organizations, then and why we're using condition monitoring, really they're summed up in these three different areas. Improve safety is always number one, that every company that we would go to, every company we would visit, safety is the number one priority. Also, if you're looking at a slightly underperforming network, you want to improve that performance, you can use condition monitoring to prevent that failure. Crucially, if you get the failing or the potential disruptive failing assets off the network before they disruptively fail, then that's cheaper than allowing them to fail. A fix before fail is always a cheaper option. Ultimately, there are companies out there, very, very good performing companies in the world, where they just concentrate on safety. Take the bad stuff off the network and everything else follows. These are not mutually exclusive. These are very intertwined objectives. So we can look at that. If we look at this particular example here, this is from a 33 kV bus bar where partial discharge has been found. So you can see in here, the evidence of PD that you would see in this is the green verdigris that you've got on the what should be nice metallic connections. And then on the shrouding of these bus bar connections, you've got the white powder and the treeing and the sort of tracking that you're getting. All evidence of PD activity that's going on in this 33 kV bus bar. So if we find that, we've taken the time to do a condition survey, we've seen that something's discharging, then we've got to take a bit of a leap of faith to take that off the network to open it up in order to do the investigation and fix that problem. So we need to take a bus bar outage. We're going to have to remove these shrouds, these connections. We're going to have replacement parts. That's obviously going to have a cost that we have to deal with. But at the same time, if we will let that to happen, as you can see here, is exactly is what happened. Now the switchgear is disruptively failed. So at this point, we're not in a situation where we're in control. So this failure has happened wherever it may be, usually 4 o'clock in the morning on a Saturday or something. You've got overtime, you've got unexpected switching to do, lost production or lost elements of the network. We've got the carbon generated from the fault area now. So that carbon, the dust, the debris has now gone up the bus bar. So it's affected larger components, maybe down into the CT chamber, down to the circuit breaker, the cable box, depending on the configuration of the switchgear.
Just had a few comments here.
Okay.
How much cheaper is it to fix before failure? And then Andrew's commented repair before failure. Cost is typically orders of
Okay, so the sort of failure, we would typically look at that for, even for a cable, if you can take a cable out of service before it fails, we work that as being usually about 1/3 of the cost of letting a cable fail, and that's usually the smallest ratio. For switchgear, we're looking at multiples. So let's say this was a bus bar on a primary zone substation, 33 kV. So a pretty large cost to take an outage on this to fix it up before it fails. So let's say call that $50,000 maybe. It's not unreasonable when you take in labor and take in parts and things like that, generation costs. If we're looking at this now, where we've got the situation, we could have an outage that lasts particularly weeks or months longer. We've got to replace these components. We've got to start looking at the cleaning. Potential what you have when you get a failure that goes into the bus bars, into other areas, is you get secondary faults. So that starts coming up. So we could be looking at multiples, 3-4 times the cost of that. Certainly when one of the companies that has done a big study on this in Singapore Power, they looked at that cost, and the savings that they were making were in that order of between 2 and 4 times the cost, possibly more than that at times, depending on the voltages that they're looking at, with the cost of that you're saving. Okay. Okay, so I'm just going to hand over. Brad's going to just do a section on partial discharge.
Okay, so what is PD? I'm just going to go quick brief overview of what is PD. So there's an international standard called IEC 60270, and inside that standard there's a definition of what partial discharge is. The definition talks about insulation breakdown, but not a full breakdown from either phase to phase or phase to earth. So it's talking about partially bridging out parts of the insulation. The defects that cause this are electrical. The defects that cause PD cause high electrical stress points, and those defects will either be on the inside of insulation or on the outside of insulation. So there are 3 main types of PD classification. We've got internal discharges, and that's where you've got some sort of split or crack or void or air gap inside an insulation layer, where discharge will build up because of high electrical stress. Then we've got what's called surface discharge, and that's where you have defects on the outside of the insulation systems. That can either be touching the surface of the insulation, or it can be very close to the insulation, and you have a high electrical stress built up across that area. The third one we have is corona discharge. Corona discharge occurs when you've got a very sharp point, so a pointy end of a lug or some sort of bolt, where there's a high electrical stress point at that area, and it effectively ionizes the gas near it, which is usually air, and causes discharge to occur. So we have 3 different types of discharge here, and there are different techniques that are more effective at capturing the signals given off by these 3 different types of discharges. So if we think about discharge a little bit more, and a good way to think about discharge is to think about physically sparks occurring. So sparks will give off light because you can see a spark. Sparks will give off heat because it's effectively a tiny little lightning bolt. It will give off a smell because it ionizes the air or the gas around it. It will give off a sound because you can hear a spark. And it will also give off electromagnetic waves. We can't see those electromagnetic waves, but there is instrumentation that detects the electromagnetic waves. So if you walk into a substation or close to a HV asset, and you can either see some sparking going on, or you can see some heat or evidence of heat. If you can smell gases that shouldn't be in there, namely ozone gas, or if you can hear discharge and sparking and arcing going on, you've very likely already found partial discharge just by using your own sensors. A lot of the time it's not that, it'll be at a very large state if your sensors can already pick it up. So we use instrumentation to find that. The instrumentation looks to detect ultrasonic sound waves that are being emitted by typically surface activity. And also we use instrumentation to detect the electromagnetic waves given off that effectively every time a spark happens. So let's go into those 4 techniques. So here we have 4 techniques. We've got what's called the transient earth voltage technique. What we do with that one is we are detecting the tiny little voltage rises that occur, that is a byproduct of the EMF that it's given off when sparks occur or when PD occurs. We have ultrasonic airborne microphones and contact probes and an ultrasonic dish that will listen for the sound or the crackling and the arcing, and corona as well. Corona will give off sound. And we listen in the ultrasonic range using these microphones to detect PD that we can't hear with our own ears, because a lot of the time our ears won't hear them. When you've got PD inside cables, a very effective way of detecting the PD is by using what's called RFCTs or HFCTs, that stands for radio frequency current transformers, or high frequency current transformers. And that is effectively picking up the EMF signals given off by a spark, and those EMF signals are bouncing up and down the cables and reflecting off different impedance changes within the cables. Another technique we use is the UHF technique. So when PD occurs, it will give off ultra high frequency signals, and we can detect that using UHF detections. Does PD occur in low voltage applications? We've just had a question through from Nathan, and typically no. By definition, it occurs at high voltages because the electrical stress is high enough at that point to give off PD signals. Okay, next slide. So handheld PD detection. So handheld PD detection, the first one is transient earth voltage measurement, or TEV measurement. So to detect TEV signals, we get we have one of our engineers here. His name's Thomas. He's holding an Ultra TEV +2, which is one of our main handheld instruments. He's holding that against the metalwork of a ring main unit there. What the instrument is doing is it's got a little transient earth voltage sensor in the end of the instrument, and it's detecting the tiny little voltage rises that are occurring on the metalwork, which is a byproduct of PD activity and the EMF activity given off by PD. So what we do is we hold that, the Ultra TEV +2 sensor, the TEV sensor, against different parts of the switchboard to detect where signals are coming from the highest. So we would detect at the cable box, at the circuit breaker, at the CT chamber, at the VT chamber, on your bus bars. Also on the outside of your high voltage cables is a very effective spot to test. When we go outside a switch room, we can test for TEV signals on underground cables going up poles, on the poles themselves, on the earth straps as well. So TEV nominally picks up internal void type PD, and where you have contact type issues where sparks are jumping across gaps. So the next so another slide here on internal void PD. So here we have the outputs of the Ultra TEV +2. So what the outputs are, we get a decibel level. That's where you can see the 38 dB written there on your screen. We also get a pulse per cycle count, and on the screen there it's written as 3.04 pulses per cycle. And that's counting up how many times per sine wave that discharges are occurring. We also get what's called a phase resolved partial discharge pattern. And on the bottom left graph there, you can see 2 waves of activity coming up, and that phase resolved partial discharge activity is showing the user where on the sine wave, with reference to your 50 or 60 hertz frequency of your network, where the PD events are occurring with reference to that. So we can analyze those pictures and figure out, you know, what type of PD is occurring, whether you're detecting noise, whether you're detecting internal void, is it single phase, 2 phase, 3 phase, all these types of things. So this one here is a case study where we have detected those TEV signals on the outside of a 22,000 volt cable that's running up that cable tray there. We've used all that data to come up with the conclusion that there is very, very likely internal void PD up on top of that transformer where there's actually a high voltage joint up there, or it could be in one of the 3 terminations that terminate onto the top of the transformer. So all of these pieces of information we use to come up with an answer. Have we found PD or not? How bad is it? What type is it? Okay, next slide, please. Okay, so the next technique is ultrasonic measurements. So ultrasonic activity occurs when PD activity is occurring. It's the sound given off by PD activity. So we use microphones, we use parabolic dishes, and we use what's called a contact probe as well to listen for effectively the sound waves that are giving off every time a spark occurs or whenever the corona is occurring. Here we have one of our engineers, it's Thomas again. He's got his headphones on and he's using the UltraTEV Plus 2 with an airborne microphone, and what he's effectively trying to do is listen into all the different high voltage chambers at a switchboard or at a ring main unit, and listen into each chamber to effectively test for sound. And we listen for sound. Once we get the sound, there we go, across to the next one. Once we detect a sound, we have to figure out whether that sound is being caused by PD activity or whether it's being caused by some sort of noise, because you do get interference. You do get other things that will emit sound in the ultrasonic range that the instrument picks up. So to help the user, we've got an algorithm built into the instrument. It will classify the noise that it's hearing as either, I should say that the sound that it's hearing as either noise, so not PD, or PD. So it does that as you are taking the reading, and it gives the user further confidence in what they're trying to test. You'll also get a decibel output. So on the left there we have 21 decibel microvolts. On the right we have 29 decibel microvolts, and that's the amplitude of the sound. You also get a phase resolved partial discharge pattern, and that's what those 2 green patterns that you can see on the left and the right there are. So I'll just play the one on the left-hand side. So this is a sound that's produced by magnetic noise. So this would have been listening to a VT, and it's the sound that the VT is giving off as it's transforming electricity. So that sound there, hopefully everyone could hear it, was heard inside a chamber, and it gave that phase resolved partial discharge pattern. The algorithm classified it as noise. It gave an output of 21 decibels. So that's the information taken from that. You also have to take into account what sensor you were using and what you were testing to help figure it out. On the right-hand side, we have a proper PD source. I'll just play the sound from that one now. So that one there is from a discharging defect, and we can hear the crackling and the arcing and sparking going on. So the algorithm's classified it as PD. Next slide, please. So here is another real-life example. We have this one here was on the side of the road at a ring main unit in Australia. We can visually see PD occurring between the 2 phases, where you can see that white discharge occurring. There's high electrical stress points there, and there's defects in between those 2 phases where there's too much electrical stress, it can't hold in the volts, and PD activity is occurring. It may also be being affected by contamination within the box, such as dust and debris and all that sort of stuff. High humidity as well within the box, maybe speeding up the process. But this discharge we could hear it with our own ears. It was at a very high amplitude. It was at 47 decibel microvolts, which is very high. We have the phase plot there that we've captured with the UltraTEV Plus 2, and this is what the sound sounded like. And we have found that one there was found visually, it was found with our own ears, but the instrument was also able to take a recording of it and help further diagnosis. The algorithm there predicted 100% certainty that the sound was being caused by partial discharge as well, so it gives further confidence, again, even though we can see it. So that's just another case study.
Okay, so I'm going to start looking at testing intervals. So you can see from the case studies that Brad has been showing there, we're getting a lot of really good results. We're getting very good certainty. Nowadays, we're seeing, you know, that we're definitely getting an internal void discharge in that cable joint. We're definitely getting partial discharge activity identified in cable terminations in that last example. The question then becomes, how frequently must I look at testing? And that's the difficult one. When I first started doing this, so when EA Technology started really pushing the use of this into the electricity industry in the UK back in the 1990s, 80s and 90s really, we started looking at maybe once every 2 years was a good starting point. One of the reasons for that is if we go back there, we're looking at very much void type problems. So compound insulated cable boxes, compound insulated chambers and oil filled switchgear. And if you're looking at a void degrading through bitumen and things like that, it's usually quite a long process before it goes into failure. As we started moving towards using air insulated terminations, so we started going to dry terminations, more air insulated switchgear, we start moving away from porcelain, going into cast resin and resin type plastic type insulation. We started seeing more and more surface type discharge occurring. At that point, you can get much quicker degradation to failure, particularly if you've got a poor environment. So nowadays, what we tend to say is that there is quite a wide variation. So some failures will occur and take a long time before it gets to failure. Some will accelerate quite quickly away. So if we look at the classic RCM type approach of looking at the P2F curve, which we got here, the point at which you can a defect can be detected to the time at which it fails. If we knew that we had a very defined period of time, say 1 year, then the RCM approach would be to say to halve that and make a testing interval of every 6 months. Unfortunately, like I say, the different types of defects tend to have much different P2F type intervals. For that reason, then really using consequence is more the approach that people are taking to determine how often, how frequent, and also the acceptance of failure. So the less frequently you test, the more probability you will have of a failure. You're reducing the probability less. So for low consequence assets, maybe once every year or once every 2 years. Medium consequence, you halving that, coming down to every year or every 6 months. For high consequence assets, then maybe you're looking at every month, every 1 to 3 months, or permanent monitoring. So EA here in Australia, we're doing permanent monitoring for people. We're also doing testing in certain critical assets where people have got known defects, and we're testing them every month, so that we can get the best warning of failure. So it's a variability, and the higher the consequence, the more the business case, the easier the business case for permanent monitoring. So let's look at an example where the P2F curve was relatively short, or P2F period was short. This is one where in the UK, EA Technology, working with one of the DNOs, had installed one of our monitoring systems. It was part of a prototype and long-term testing. Nobody had really taken the trouble to instigate the communication. So nobody was actually looking at the data. And this is a classic case of people can see a project to monitor switchboards and see the project as putting the monitor on, whereas really the project starts when the monitor is installed, because you've got to be looking at the data. It was a high risk, quite a critical switchboard. It was near a river. It's a particular type of switchgear that doesn't particularly like high humidity and has been known to discharge. So we installed the monitor in November 2014, and at the end of July 2015, we received a phone call that the substation had blown up, and could we investigate the reasons. So the substation blows up and people say, oh, we've got a monitor on that. Possibly you want to do it slightly different to that. So the failure investigation team looked at it, and we've got this black crispy switchgear here. And then we looked at the data. So the monitor luckily survived, the switchgear potentially hadn't. The monitor survived, so we've got that information that we can then look at to see how it's progressed. So if you look at the graph here, in February, March, then we got very little going on. Towards the end, so the 29th of March, we've got a step change in activity. So the ultrasonic alarm level has been breached if we'd have had the alarm level instigated and communications enabled. That's then gone up. So by the time we're into middle of April, May, we've got a pretty high, steady level of about 40 decibels of ultrasonic. And it stays there until the 28th of July, pretty flat. So you don't often get an upward trend. So trending ultrasonic is actually a difficult thing to do. So by the 28th of July, so 3 or 4 months later, we've got a disruptive failure. So if we'd have gone in for an annual test, and we'd have gone in for that annual test January, February, or early March, we wouldn't have seen something. If we'd gone in sometime between the 1st of April and the end of July, we would have seen the problem. We could have dealt with it if we'd have dealt with it quickly enough. So the consequence of that was a large part of the city was left without electricity for about 8 hours. So the SAFEs, or in the UK as the terminology is, customer minutes lost and customer interruption fines, totaled over £300,000, so around 600,000 Australian dollars. You've obviously got to replace the assets, and you've got to change all that direct cost on top of that. So a monitoring system would have given about 3 months worth of warning to allow that change to happen. And a partial discharge survey on an annual basis may be a 1 in 4 chance of detecting that. And for that reason, with that sort of critical asset, you can see the cost benefit of installing permanent monitoring. So where does monitoring, what does it give us in terms of benefits? And obviously it's permanently there, so it's given us better capability of detecting those short P2F failures. It's also installed when we're under different environmental conditions, different network conditions, and also, of course, less labor intensive. Like I say, at times we're going into particular substations every month or every 3 months. If you're going into a same substation month after month, generally or potentially detecting nothing, the veracity of the survey has got a tendency to slip. You start becoming blasé. You stop paying quite so much attention of that. Whereas obviously a permanent monitor is doing there and sitting there and doing its job. So let's look at a couple of examples. This is one where we've got 2 sources of TEV depending on the time that you're testing. So the blue line is a nice constant source of partial discharge activity, and the orange line is a higher one that's coming in and out based on either network conditions or loading or something in that particular nature. You can see that actual one is going up to higher levels of activity when it is active. So depending on the time of day that we're testing or which day we're testing, we could miss that orange source of activity. Looking at an ultrasonic example, surface discharge will be much more affected by the relative humidity in the atmosphere compared to an internal void where it's contained within the insulation. So in this particular one, you can see if we went into our substation on the 4th of September, then we'd find nothing. We go in there on the 5th of September, and during the 5th of September, the humidity is gone up there. It's increased above the 60%, up towards 70% RH, and the discharges started off. By the time that starts then falling by the 6th of September, again, we've missed that. So these environmental conditions can trigger discharge activity. Sometimes if you've got lots of tracking, it can be surprising how degraded the insulation is, which is still coming in and out and effectively stopping when humidity is getting lower levels. So that's the sort of thing, again, the benefit of a monitoring system. So the next case study shows you a similar thing where we've got a discharge happening and it would have accelerated through to failure, except this time with the prevention, the monitoring and the activity is prevented failure. So this particular instance was a large switchboard, so it's 68 panels of 11 kV switchgear. Monitor was permanently installed using a transient earth voltage and ultrasonic sensors. You can see the top graph there. We've got about 18 months of basically nothing going on, and then all of a sudden something kicks up at the end. So if we look at this graph here, if you look at the bottom graph, that's 4th of August, that something happened, and of course that's Friday. So Friday morning we received the indication that the discharge has started triggering, and we phone up the electricity company in this particular case and indicate that we've got a problem happening. So at that point, we know that we're going to have a little bit of time. So a planned outage is an outage is planned in. So 2 weeks later, there was an outage planned in to go and investigate. We actually went into the substation around this just before that happened, and we're able to take a handheld survey or handheld measurement, and you can see that, and again on the Ultra Plus is showing there, which is 2 phase locked 180 degrees apart clusters of activity, which indicates PD, and the sound clip which isn't playing, which was again indicative of PD, and the algorithm was classifying that as partial discharge activity. Okay. Okay. Okay, so the VT was taken out of service 2 weeks after we initially detected it, and you can see we're in a bit of a state here. So we've got major cracking on that cast resin component. We've got burning happening, burning and pitching, soot and debris building up. So we've got arcing taking place on here. How long would it have taken to fail? That we can't be 100%, but small number of months, maybe a few weeks more than this. So let's just call it, again, we've possibly got a 1 in 4 chance of detecting that during an annual survey. But in this particular case, we're monitoring it, we've taken it out, we've had no disruption to the network, so no unexplained outages, no network problems, taken that out, prevented that. So that justifies the monitoring of that very large switchboard for numbers of years. So why do people install monitors? And it's really comes for a number of different things, really. So critical switchboards, high consequence, which is what we've talked about. If you know that you're going to have to replace an asset soon, it takes time to get that off, and you're looking at extending the life during that period. So extending the life of the asset or away by de-risking it. Of course, staff safety. If you're working on one bus bar and you've got the other one live, people are in that switch room for an extended period. People put monitoring on the other half of the switchgear. If you're looking to extend the life of the asset, then deferring capital expenditure is another driver behind this. So people are using all these different reasons for installing monitors, which is why more and more monitoring is going in nowadays. Just one example to show you the level of risk that can be reduced by putting a monitor on. So this is one that we did for one of an industrial customer. We did a benefit or an analysis of the risk that they were running for a switchgear failure on a critical switchboard. And what we've got is 3 classifications of failure here. Catastrophic failure is shown in yellow. A degraded failure, so relatively contained, is shown in grey, and an incipient failure is the one where we've gone in and we've been able to take it out. So the previous case study was an incipient failure. There is some cost to go in there to look at the VT, take the VT out, replace the VT. But what we're trying to do is reduce the disruptive failures, catastrophic failures, and drive them down into the orange levels. So you can see, if we look at the third block of the graphs here, what we've got is, with a monitor on, we're driving those, driving that yellow section down to being much smaller. It increases the orange section, and that's for a degraded bit of or a piece of switchgear, and basically at the end of its book life. And you can see the risk that that is running with a monitor on is actually less than the risk of the previous period where it was going through its the main part of its life. So putting a monitor on an older switchgear means that it will be running less risk than it did for the many years it was running successfully without monitoring on there. So it's a reduction in risk that helps you justify that extension of life and the capital expenditure.
Just had a question, Neil.
Okay.
Are there faults that PD cannot detect?
There are faults that PD cannot detect, and for that reason, on the graph that we've got here, you can see that we're not completely decimating by putting the monitor on all of the yellow failures, and we're not completely decimating all of the grey failures. So there will be certain things, the mechanical issues that may happen that will cause disruptive failure. The statistics would indicate that roughly 1 in 8, so 80 to 85% of failures are associated with partial discharge activity. So there will be a proportion of failures that don't occur, but if you're going to do one thing and one thing alone for switchgear or for cables, then partial discharge is the one that will get you the most of those failures and reduce that. But as we're showing in this graph here, there will be some that would be left behind and not detected. Okay, Brad?
Okay, so Astute HV Monitoring. I'm going to take you through the hardware firstly. So we've spoken a lot about the monitor and monitoring itself. Can I just maybe turn that just so we can see what's under there?
All right.
Yeah, so we'll talk about the hardware. So on the right-hand side there, you can see two pictures. The top picture is the accessories and the nodes of the hardware, and the bottom picture is the hub. It's a central hub. So what you have is a fully integrated modular system that can be extended to cover how big a switchboard you want to cover. It can be brought back down to if you just want to monitor to a small section of area. So all the nodes effectively get daisy chained up. To install the system, it's non-intrusive. All the sensors attach magnetically to the outside of your switchgear. So you can move them around. There's no drilling, there's no bolts, anything like that, as long as your metal is ferrous, which it usually is. There's no shutdown required to install the equipment. We put it on the outside of the equipment. So the sensors that are used within the equipment is we have TEV sensors inside those blue nodes that you can see on the right-hand side. We also have designated TEV sensors, and we have designated TEV aerials. And what we do with the aerials is we set them up around the room, usually on all four corners of your switchboard, to detect any external noise or external EMF waves that are coming through that look like TEV signals to the system. We also have ultrasonic sensors. So that black sensor you can see in the top right there is a microphone that you can move around. It's the exact same microphone that the handheld equipment has. And all the TEV sensors also have the same TEV sensor in it as the handheld equipment that I went through earlier. What we do with those microphones is we focus them into each of the HV chambers, into your cable boxes, into your buses, to listen to the spouts behind your circuit breakers, so your cable spouts and your bus spouts, all those types of areas, to listen to any crackling or arcing or sparking that's going on. We have RFCTs that we can attach to cables, so we put them on the outside on the screens of your cables to detect cable PD. We have temperature and humidity sensors that will log the temperature within the room and the humidity within the room, or at the location of that sensor. So you can put them in different spots of the room, and it will log all the temperature and humidity as it goes along. We have external comms. So what we usually do is we plug in a 3G or 4G modem to the hub, and that acts as a standalone communications link, so it doesn't have to interact with your company's what's it called, LAN, and so there's generally no corporate network issues and cybersecurity issues because it's completely separate. So the hardware can either be purchased or it can be loaned with us. So the next one here, the next slide here is the service that we offer. So we call it the Astute Monitoring Service. So if we are to deliver this service, what we always do is we come out to site and we conduct a PD survey of the switchgear that we're going to put the monitor on, and that's for two reasons. The first reason is to figure out if there's any PD happening at the time, capture all the phase plots, capture all the information we need to about it, and then secondly, we focus the sensors to be able to detect and monitor the PD activity that already is there. And then what happens is we monitor from there. So we will monitor the PD activity remotely. The data that is being logged by the monitor gets stored locally within the machine, and it gets uploaded to the cloud server. If a PD event occurs above set threshold levels, we will receive an alarm, and then our analysts will look at that alarm, figure out whether it's a true PD event or what the next steps are to take if it is deemed to be PD. Then we inform the customer, whether that be via email or phone call or however the customer wants to be informed. We then move from there and we continue to monitor the situation. So until they can, get a shutdown and have a look at it. All that time they receive the expert advice and guidance from us. They can ask us questions at any time. And we also give reports. So we will do reports at set intervals if that's how we want to set it up, or we can also do exception reporting, and that is effectively giving you guys a call when something's happening. So the benefits of monitoring. So your switchboard will be monitored 24/7. As Neil mentioned earlier, you do get intermittent signals coming through that can be caused by changes in humidity. It can be caused by network events such as high voltage switching, too much load, or not too much load, but load flows can affect PD activity as well. And because everything's time-stamped and everything's logged, you can actually cross-reference it with things that are going on in your network to see what's kicking off this PD activity. It will reduce your risk of failure of your switchboards. It'll help you make better decisions in terms of, righto, we have PD here, what are we going to do about it? How are we going to manage it? It will take the onerous of PD monitoring off you and put that on us so that you guys can do what you need to do, whether that be running your network or digging coal out of the ground, whatever it is that your company does. Help support your money decisions, and it will help give maximum availability of your assets. We have a few more case studies here of what we've found in the past. So this one here is a 11 kV switchboard. It is where we have conducted a benchmark survey. We've identified PD within the cable box that you can see there highlighted in red, pitch-filled cable box. We straight away advise the customer that there's a high level of PD inside that cable box. What we then advise them to do is shut that cable box down to reduce the risk, and that's what they did. And in the top graph there on the left-hand side, you can see that the activity has dropped off as soon as they have taken that asset off the network. The bottom graph is the phase resolved partial discharge pattern that was captured by the Ultratech +2. And within that, we can see that there's multiple discharge defects on multiple phases by analysing that. Okay, we'll get to the questions in a second, I think.
Yeah, we've got a few questions to answer.
Yeah.
Once we've gone through this case study. Yeah.
We will get to the to the questions. So here's another case study. So this is a defect at a VT. So this is a rackable VT on an 11 kV switchboard. This one here, the main reason that this one, or not the main reason, but this one occurred on Christmas Eve. So we found the PD activity via the monitor on Christmas Eve. Within 2 hours, we'd notified the customer, and then within another 2 hours, they had people down there and they'd switched out that VT. The reason that they switched this VT out so quickly is because they had skeleton staff that were going to run the network over Christmas. They didn't want a failure on Christmas Day or Boxing Day or anything around there. And that reduced their risk over the Christmas period. When they pulled the VT out, the damage was not extensive, but it was causing PD activity. In the top right-hand picture there, you can see one of the bushings that makes up the VT, and in the bottom right of that, you can see some it's like a light brown area, and that's where there was a bit of damage to the bushing from when it had last been racked in. Also, the spring tension on the contact wasn't set correctly, and there was a bit of a gap behind the spring, and that was causing PD activity to build up inside that connection, and it was giving off, PD activity at that point. And this is our last case study. This is an air insulated cable box. So this one here, we installed a monitor on the whole switchboard here. We conducted a benchmark survey with the handheld equipment. We didn't find any PD signals within this cable box at all on the day. But 3 months later, we saw a spike in activity, which is highlighted there by the red arrow on that graph. The spike in activity occurred. It didn't go up to high levels, but it was at a medium, low towards medium level. And we notified the customer. We said, look, we'd like you to go down there and just confirm what we're hearing. And so the customer went down there, one of their engineers with an UltraTEV +2. He listened into the cable box with an ultrasonic sensor, and he confirmed that PD was occurring inside there. He was comfortable to let that sit for a little while because they had a lot going on that network. He said, if things get worse, let me know, but I'm booking an outage as soon as I can. That outage occurred 1 month later. When they took the outage, they opened up the cable box and they found what you can see in the bottom right-hand picture there, where you've got 3 phases coming up into the cable box. 2 of those phases were too close to each other, and that was causing discharge activity to occur across the phases. So what we were able to do here, or what they were able to do, was we picked it up very, very, very early, and it was a very easy fix for the customer. What they were able to do was increase the clearances between those 2 phases by separating them. They were able to clean up that area, and they found that there wasn't extensive damage there where they needed to replace heat shrink or replace the termination itself, which would have been a very large job. So they were able to find it early, an easy, quick fix relative to a failure, or relative to leaving it there for months and months and months, and it really ate away at the insulation, and they'd have to, if they did find it, they'd have to replace it anyway. So that gave good value with that one.
Okay, we've got the summary there, but let's just have a look at some of the questions that we waiting to answer. So if we go, how right, okay, we've done I think there was one earlier on, Tommy.
Oh, was there one from Tommy?
Tommy,
this? Here.
With fixed PD monitoring, how and where would you fix modules to capture PD? That's quite an interesting one. So for transient earth voltages, TEV tends to travel, so it travels across the surface. There's the sparks, due to the skin effect, will travel quite readily across the surface of the metalwork. So we typically only put 1 TEV sensor on each cubicle, or every other cubicle if we're trying to reduce cost and got very large switchboards. So what we can do, because it's a relatively simple case to replace, to reposition due to the magnetic nature, we usually put 1 on an appropriate part of the switchgear depending on the type. So we make an assessment of the type of the switchgear, the construction. Sometimes we'll put two sensors, but generally it's 1 or 1 every other, and we'll see where signals will go. So that's how we'll make an assessment on the TEV, because it will transfer. With the ultrasonic, it's a slightly different thing. Ultrasonic sensors have to be pointing into the right chamber. So if we're pointing into a cable box and we've got PD in that cable box, which is similar to what Brad just showed there, then that's not necessarily going to be the same sensor that would pick up something in a bus bar. So we would typically put one in each of the air chambers that we're interested in, and maybe a few on the bus bars. Because bus bars generally don't have segregation between them, then one or two per section of bus is usually enough to cover the bus, and then the other ones that we're pointing in towards air-filled chambers. On the switchgear that we saw failed in the UK, then the biggest cause of the failure was typically tracking on the circuit breaker, so you would be pointing towards the spouts in that particular instance there. So how and where we place the sensors is dictated to a certain extent by the type of switchgear, and that's where we usually have knowledge of that. How often does the Astute need to be calibrated for its accuracy? Again, an interesting question. Formally, we often calibrate things every 2 years for an installed monitor, or we do a check on that. The system itself does automatic checking on this. And there's another fundamental question. Some people don't actually go for a calibration once they've installed a monitor. You know if it's working or not. It has got its auto checking. And the other aspect is what are you really interested in the exact number? Is it 23 dB or 24 dB? Or you're interested in the alarm capability and the function and what it's changing and trending? So if one of the sensors were, for example, to drift, so it's reading 1 dB out, fundamentally it's not realistically going to make much of a difference in terms of the answer and the diagnostic. But typically you can go in there, say every 2 years, and check each of the individual sensors. Does one node support one RFCT? On the particular nodes that you saw in the pictures, where you've got two TEV sensors, two ultrasonic, that particular node supports one RFCT. We've also got another node which supports, it's a standalone cable node which will support 3 RFCTs. So you can have a combination of those in the chain, so you can make sure that you're testing the cables, particularly when you've got multiple cables per phase on some circuits. Have we ever had a case where we've opened a switchboard, a cable, and found nothing wrong, or vice versa? That's a good one as well. That's from Roger, I think, on New Zealand.
Yep.
So when you're finding TEV activity and you open something up, you often don't see anything because it's in the inside of the installation. So you'll open up a CT chamber, for example, on Rayroll LMT, and it will look absolutely perfect, but inside it's discharging. So sometimes you can't see it. The compound insulated cable box that Brad showed on the case study, it'd be very difficult to actually find a problem in that. By the time you melted the compound out, it may have gone, although it can be. So sometimes it's difficult to find something. Early stages of ultrasonic can be difficult to find at times. It will make a mark. If you get an ultrasonic sensors, it will be on the surface, so it will be affecting insulation. We often you have to use strong light sources, mirrors, things like that, to make sure that you're assessing something. So the earlier you go in there, the quicker the fix, but at the same time, the less damage that has been done for you, enable you to see it. So you do have that thing to think about. We haven't actually had a failure on our Australia, New Zealand monitors, touching wood. Yeah. We've prevented quite a few. We haven't actually had a failure occurring on our watch. It could happen. Have to say it could happen. You could see, we're not claiming nobody. If anyone does claim that Partial Discharge will find every single fault, then they're telling lies. There will be elements of failure out there which we won't see before it fails.
Quick ones.
Yeah, often the quick ones. Cables, another one. If you had a defect inside the solid element of the XLPE cable, that potentially will accelerate failure very, very quickly before the monitor really has had chance to see an upsurge as well. So that's another thing that could potentially cause problems.
Yeah. Got one here from Jason Murray.
When PD is found, what's the next step?
Do we contact you for analysis?
Yeah, that's
ourselves?
Or do it yourself. That's either or. That's what we tend to do. So on our monitoring service contracts, we're there as a point of call. We understand the switchgear, we understand the types of defects, and we can help with that next stage. We don't always need to do that. We can talk people through that, guide people through that. So it happens both ways, and it's usually a collaborative thing. We would never walk away from a set, because the one thing that you want as an industry, what we all want, is to learn from things that we've found. So if we've got an element of, if we find discharge signals, somebody opens it up, we actually want to know what they saw, and we want to learn from that to improve ongoing the sort of service and the diagnostics that we can make. 6 months annual for medium consequences when you're referring to online periodic testing, i.e. testing. Yeah, we're not talking online. When we're talking about the periods, we're effectively talking online. It's quite interesting. In Australia, there was lots of companies who would say that they were going to test switchgear every 12 months offline. I don't think it really happens as often as all that anymore. You've got to also understand, if you're testing offline, you're taking switchgear out of service, you're potentially not testing the cable termination, because you're the capacitance of the cable. So you wouldn't be able to test cable termination, the VT, and they're two critical areas. But we're talking online in terms of our periods, yeah.
Just got one last question here from Andrew Hill.
When I recommend to a client this Astute should be installed, what is the typical ongoing cost of monitoring in 2020? Yes, the slides are available for download. The ongoing cost is not excessive. It just depends on the number of panels and everything else. So it can be down to a couple of thousand or $1,000 a month for a certain switchboards. It can be more than that. So it really does depend. So if Andrew, if you wanted to give us an indication of an SLD, we can give you a very good. We can give you an indication very quickly on that. But you're looking at a small number of $1,000 per switchboard per month is typical for a completely leased system with full analysis and everything else. Okay. A copy of the slides will be made available. We also have on this last slide here, we've got our contact details. So just starting to chuck now. So Brad and I will be more than happy to take questions, take calls, and go one-on-one with any of you if you want to go into any depth of any of the topics we've covered here.
So you can.
I think everybody gets to see the answers to the poll. So we've got expert users, we've got and people in the middle, which is where you would expect most people to be, as well as people who are learning out. So some of the guys who have got very limited experience, we've gone over that theory very, very quickly, and we're going to be very happy to do a webinar on more of the fundamentals should they be required. So the topics that people are interested in, Brad, on the poll.
Sorry.
Yeah, everybody's always interested in PD case studies and seeing the black and crispy switchgear, particularly if it's not yours. So yeah, we've got lots of case studies that we can present. So we could put a webinar together on that. So we will do that for you. It's still moving, so people are still voting. Oh, it's neck and neck. Handheld PD instruments as well. They would go hand in hand. So we could do handheld instruments and the case study you find on them as well. So we'll take note of the final results of the poll and feedback that we're getting, and we will we will publish and let everybody know what the next topic will be, and that will be done shortly. And thank you for all your thank yous.
Yeah, what I'm saying, thank you. Thanks, guys. Thanks for logging in.
Okay.
No problem.
Stay safe.
Stay safe,
And,
everyone.
we look forward to hearing.
Yeah. Any questions, just shoot them through and we'll get back to you. No problem. Sure.
Bye.